In this video, I want to talk more about matrices. We've used matrices for one purpose. We use matrices to solve systems of equations, and they're very efficient at that, but that is not the only purpose of a matrix. A matrix is just a big storage body of information. We've already seen what they look like, right? They're these series of numbers and letters written in brackets. They just store large sets of data. So let's get more into the details. Let's see how these things really work. So first thing I want to define is the order or dimension of a matrix. The order or dimension of a matrix is the number of rows and columns, essentially its size. Always lists the rows first and then the columns. So let's just write out a couple examples. Let's say I have a matrix that looks like this. So if we look at this matrix, the order of this matrix, we would look at the number of rows and columns. We have 1, 2 rows, we have 1, 2 columns. This is a 2 by 2 matrix, and that's how we would write the order or the dimension. That one was easy because it had the same number of rows and columns. So let's say we have matrix 5, -2, 1, 7, 9, 5, -3, and 4. This time we have a different number of rows than columns. We see we have 1, 2 rows, we have 1, 2, 3, 4 columns. And so the order of this matrix would be a 2 by 4. And of course we can do this over and over again, right, for any size matrix. I will point out this one that we started with, the 2 by 2, that is called a square matrix. Anytime that there is the same number of rows and columns, that is a square matrix. That makes sense. Square means the sides are the same. Let's build upon our knowledge and terminology. Matrices are made up of elements in each of their cells, right? That's what each of these things is called. Each of these is a cell. So 5 is a cell, 9 is a cell, so forth. We can use the lowercase letter to match the uppercase letter of a matrix. So a lot of times when we define matrices, I didn't do it here, but we would define these matrices using capital letters. And we've seen the value in naming things before. That's the reason we name functions f of x, g of x, h of x, because then we can refer to a single function when we have maybe 4 or 5 listed. Labeling our matrices allows us to do the same thing. It allows us to call upon a certain matrix out of a list of matrices when we were trying to work with just that one. And functions we tend to list with that f of x, g of x, and we have that kind of consistent notation. Matrices, we tend to list them with uppercase letters, and we tend to concentrate on the first half of the alphabet. The back half we reserve for variables. X, Y, and Z we typically reserve for variables. So we can have variable matrices too, or unknown matrices. So typically you'll see matrices labeled with those uppercase letters. We can think about the elements inside those matrices as being the lowercase. So the elements here are little a's, and we're going to see how we can apply that in just a second. We can label those elements in accordance to their row and column. So let me define a matrix. We'll call this one, we'll use A again. I'm going to have the numbers 1, 4, 9, 2, 0, and 6. And I'm going to call upon certain elements based on their position. So let's look at the element A1, 3. So what this is telling me, this is a subscript here. This is saying I'm looking for the element in matrix A that is in the first row and the third column. The same as with the order, we always list rows and then columns. So the first row, third column would be this 9 right here. If I were to look at A sub 2, 2, that is saying the element in the second row, in the second column, second row, second column, that would be the 0. What if I had the element A3, 1? Well, that's saying the third row. Well, wait a minute, we have a problem. That doesn't exist because the matrix just doesn't have that third row. That's impossible. Why are we trying to talk about something that isn't there? So we can refer to the elements using this notation. What that also allows us to do is to write the matrix A, to call it in a slightly different way. We know that those brackets indicate a matrix. And by writing A with a subset I and J, we're saying we're writing out a matrix with elements of A in each of their rows and columns, where I is the number of rows, I'll just say the row, and J is a column, as we are accustomed to seeing. But by not specifying it like we were here, and by putting in brackets, I'm saying let's call upon all those elements regardless of what row and column it is in. And the reason I wanted to start with this is because this is going to make it easier to do operations with matrices. So the first thing that I'm going to look at is adding and subtracting matrices. Now, the first thing that has to be true in order to add and subtract matrices, their orders must be the same. If the orders aren't the same, then we can't add them. It's as simple as that. In order to add two matrices or more, they have to have the same order, same dimension. So if we want to add matrix A plus B, or subtract, doesn't matter, right? We're going to take all those elements, all the aij's, we're going to add it to all the elements from the matrix B, the bij's, and we're just going to add each of those elements in their respective cells. Put the ij in there. So we are adding elements in the same cell. So let's take an example. Let's say I have matrix A, and I'm just going to, rather than defining them, I'm just going to write them down. So we have 3, 1, 9, 2, negative 2, 3. And I said we could add, subtract. I should note here we could add or subtract. We just need to do whatever the operation is telling us to do. And then my second matrix, we have 5, negative 1, 6, 0, 2, negative 3. So in this case, we're adding. So clearly we're adding the elements of the matrix. And so I'm going to just start with that. The orders, make sure the orders match. We have a 2 by 3 matrix here, we have a 2 by 3 matrix here. So the orders do match, we can in fact add these things together. So I'm going to take my 3 and add my 5, it's going to give me 8. I take my 1 and add my negative 1 because they're in equivalent positions, the first row, second column. 1 and negative 1 is 0. 9 and 6 give me 15, those are both in the first row but in the third column. Moving to my second row, I see that I have 2 and 0 in the first row, that would give me a 2. Negative 2 and 2 is going to give me a 0, and 3 and negative 3 will give me a 0 there. So this is my resultant matrix when I add those two initial matrices. Like I said, it works for addition and for subtraction. So let's take the same two matrices, and this time I'm going to subtract. So call that example 1, this will be example 2. I'm going to subtract the 5, negative 1, 6, 0, 2, and negative 3. Well, we are subtracting, so I'm just going to remember to subtract elements in the same position. 3 minus 5 is going to give me a negative 2. 1 minus negative 1 gives me a 2. Minus negative turns into a positive. 9 minus 6 is a 3. 2 minus 0 is, it's a 2. Negative 2 minus 2 is a negative 4. 3 minus negative 3 turns it into a positive. That's going to give me a 6 there. And so there would be my subtraction and addition of two matrices. Relatively simple. Addition and subtraction of matrices is very nice because all the properties that we can think of holding true with just real numbers, adding, subtracting real numbers still holds true. So if we think about the commutative property, commutative property says we can switch things around, commute to move. So A plus B has to be the same as B plus A. For addition or subtraction, doesn't matter, as long as we keep the signs with the respective elements. Commutative property still holds true. The associative property. As long as matrices can be added, it does not matter the order in which I add those. So if I have A plus B plus C, I could have also said A plus B plus C, and then of course I could reorder those. That is still true. I still have an additive inverse. Meaning I can take a matrix, let me just switch over to the A notation, I can add its negative matrix, and that has to give me the 0 matrix. And notice I said the 0 matrix is not purely 0 because remember we were creating a matrix. That matrix may be full of zeros, but it is going to match in order to the initial A's. We have an additive identity. What that tells me is I can take a matrix A, I can add the 0 matrix to it, and I have to get back to matrix A. Again, this 0 matrix has to match in order. We can't take a matrix A, let's say we have 1, 2, 3, 4, I can't say let's just add 0 to that. They don't match, they're not the same order. This would have to be a matrix with 2 rows, 2 columns. And now we could add those two things together. So why am I talking about all these properties if they continue to hold? That seems pretty basic. Well, they're not. The properties aren't always going to hold mathematically. Just because we've had the commutative property before doesn't mean it's going to hold true for every other mathematical operation. We're going to see examples of that in this video, so bear with me. Let's move on to scalar multiplication. Scalar, a scaling factor or a scalar. We've seen scales before in life, right? Think about a map. On the corner of maps, there's a little scale down there. It says, hey, this 1 inch represents 5 miles, or whatever it would be. Model cars or model airplanes, same idea. You might see a 1 to 24, something like that. That's representing 1 inch on this model represents 24 inches on this real life car, whatever that scalar might be. So it's a way of growing or shrinking things so that everything proportionally remains the same, but the numbers are growing bigger or smaller. And so let's let C just be any real number. Be any real number. Well, we can take C and multiply it to any matrix A by simply multiplying it to each of its elements. So C, A, I, J inside the matrix. And we'll do an example of that. Let's say we have 2 times the matrix 1, 3, 4, 9. Notice I said nothing about order because the scalar is just a multiplying factor. It's not another matrix. Matrix multiplication is going to be much more challenging. When we multiply these together, we multiply the 2 times the 1, that's 2, 2 times 3 is 6, 2 times 4 is 8, and 2 times 9 is 18. We just, in a way, kind of think of it as distribution. We distribute it inside the matrix. And that's pretty easy process because we, again, are just taking the elements and looking at them element by element. We're not talking about matrix multiplication yet. We'll get there. So if we think about the properties that are true for scalar multiplication, we have the multiplicative commutative property. Does not matter the order in which we multiply. So C times A is equal to A times C. We have the associative property. C times D times A, where D is just another scalar, is equal to C times dA. C and D, both scalars. And that's really not even true through properties of real numbers, properties of matrices rather. That's just true through properties of real numbers. We know how real numbers work, so that's really nothing new. We have the distributive property. If we take C times A plus B, two matrices A and B, notice the C is lowercase, that'd be equal to CA plus CB. But we actually have another form of the distributive property. If we have some C plus D times the matrix A, we can write that as CA plus DA. We can distribute a matrix across two scalars or scalar across two matrices. It works the same way. Again, C and D both being scalars here. We have the multiplicative identity. Identity. 1 times anything is itself. 1 times A is just A. Notice there is no multiplicative inverse. There's no way for me to take a scalar, multiply it to a matrix, and get back to just 1. So we've lost a property for multiplication. There's no way for me to take just a set number, multiply it by matrix, and get back to one single number. So there's no multiplicative inverse. Let's move on to matrix multiplication. This is going to be the most challenging operation that we have done, and this is the hardest thing we're going to do with matrices in this video. Matrix multiplication is the most challenging because to think about what it means to multiply things together, we were saying 3 times 6, we were saying we have 6 3 times over. We're saying we have two matrices being multiplied by each other. Those matrices have many different things going on. The different lines might represent different equations or different different scenarios, and then each of the different columns represents a completely different scenario or different variable entirely. So somehow we have to scale each of those things up in a logical way, all kind of at the same time. So I'm just going to jump right into an example, but the first thing I do want to note is that with addition and subtraction, we said the orders had to be the same. That is not true of matrix multiplication. If matrix A has order m by n, and B, matrix B, has order p by q, then to multiply A and B, multiply A times B, n must be equal to p. And notice the order here matters. And I'm kind of giving away one of the properties already, but the order here matters. I'm not saying B times A, I'm saying A times B. That's very deliberate. Then what we're saying is those inner orders, whatever we're multiplying, those two things have to match and has to be the same as the P. So we're going to take a few examples. Let's say we have the matrix 1, 3, 2, negative 1. I want to multiply that by negative 2, 0, 4, and 5. Now this first one I'm going to write out in all its details, and then we will kind of speed it up as we go along. The key to multiplying is I have to multiply an entire row by an entire column. Always multiply row by column. Start at first position. Row by column, always a row by column, right? We said the same thing with the order. So that really that's the first thing I should look at, the order here. This is a 2 by 2 matrix. This is a 2 by 2 matrix. So we see those inner numbers match, we can multiply these two things together. Row by column. So I'm going to take a row and I'm going to multiply it by the entire column. I'm not just matching their positions, because that's not how matrices work. They're containing these things called vectors. We haven't really talked about vectors in this class. They're containing these vectors or these arrays. They've got to work through that entire array of numbers. They can't just take one number and match it to another number. That's not how they're working. So I'm going to start with this first row and I'm going to multiply it by the first column. I'm going to go through the whole thing. I can't stop halfway through. So I'm going to take 1, multiply it times negative 2. And I'm going to add to that the 3 times the 4. First row by first column. First position, second position, second position. That finishes that first cell. I've not multiplied the first row by the second column yet. So I'm going to go over to the first row, second column. I have 1 times 0. I'm going to add to that 3 times the 5. First row, second column. I'll move to the next row and next column. So now I have the second row. Notice I'm in the second row here. First column, I'm going to be in the first column here. I'm going to start at the beginning of the row. 2 times the top of the column is negative 2. I add to that negative 1 times the 4. Notice I started at the first position of the row, first position in the column. I've always got to start at the very left and the very top, always. Now I'm moving to that second row, second column. I'm going to take my second row, second column. Again, I have to start, even though I'm in the second row, second column, have to start at the beginning and at the beginning. I have 2 times 0 plus a negative 1 times a 5. And so now simplifying these, we have negative 2 plus 7, that's going to give me 5. Let's try that one more time. Negative 2 plus 12 is going to give me a 10. And then we have a 0 plus 15 is going to give me 15. Clean that up. So we have 10 and 15, and then we have negative 4 minus 4 more is negative 8, and 0 and negative 5 is negative 5. And so that would be my resultant matrix. Let's do another example. This one I'm going to make a 3 by 3. So my numbers are 3, negative 1, 4, 0, 2, 1, 5, 3, and 4. I'm going to multiply that by the matrix. We'll do 1, 2, 9, 7, 1, -3, 0, 2, and 1. And I'm just randomly choosing numbers. That's all I'm doing. I just want to do an example to see how this works. All right, so this time I'm going to move a little faster. Last time I just wrote down everything. This time I'm going to kind of multiply as I go. So I'm going to start in that first position, first row for first column, which means I have to start with the first row, first column. So I have 3 times 1. That's a 3, plus -1 times 7. It's a -7. 4 times 0, that's a 0. Notice how I have to move the whole way through the row, the whole way through the column. Now I'm going to move to the next cell. First row, second column. Notice how I'm in the first row, second column. So I have 3 times 2, that's 6. -1 times 1, it's -1. 4 times 2 is 8. Now I have to do the first row times the third column. I have to make sure every row hits every column. So I have 3 times 9 is 27. -1, -3 is 3. 4 and 1 is 4. Now, really, if I was going to continue doing this on my own, I would just keep moving cell by cell. But I'm going to jump around a little bit just because I want to show you how the position in my result matrix, or my final answer here, does determine what I'm doing. So just for the fun of it, I'm going to move to this cell right here. This is in my third row, my second column. So what that tells me I need to be doing is using my third row and my second column. I'm going to multiply these two things together. 5 times 2 is 10. Moving over and down, 3 times 1 is 3. And then 4 times 2 is 8. That's what would be what I get. Continuing to jump around for no reason other than illustrative purposes, I'm going to move to this cell next. Well, this cell is in my second row, third column. So I'm going to take my second row and my third column, and I'll multiply those together. I have to start at the beginning. 0 times 9 is 0. 2 times -3 is -6. And 1 times 1 is 1. And that's next, that would be that cell. Let's do one more random jump. We'll come right over here. This is the third row, first column, so I need to be using my third row, first column. 5 times 1 is 5. 3 times 7 is 21. And 4 times 0 is 0. All right, I'm going to just go ahead and finish out my matrix moving how I traditionally would, or if I wasn't just jumping around randomly. We'll just come to this next cell that's open. So this is my second row, first column, so I'll have 0 times 1. That's 0. Then I have 2 times 7, that's 14. Then I have 1 times 0 is also 0. Then I have my second row, second column, second row, second column. 0 times 2 is 0. 2 times 1 is 2. And 1 times 2 is 2. And the last cell that I need to complete is this third row, third column. So I'm going to take my third row and third column. I have 5 times 9, which is 45. I have 3 times -3, which is -9, and I have 4 times 1, which is 4. Now just cleaning all of that up, 3 and -7 will give me a -4. That'd be 5 plus 8 is 13, 34. And then here we have 14, 4, and -5. And then we have 26. That would be 21. And 36, that was a 4, I believe. And yeah. So 36 and 4 would be 40. And so there would be my result matrix. Let's do a couple other examples. I'm going to name them this time. Let's call it matrix A, the matrix. Let's do 1, -2, and 5. And matrix B is equal to 4, 3, and 0. Now I want to see what I get when I do A times B. So I'm taking this 1, -2, 5. I'll multiply it by 4, 3, 0. Now I didn't talk about the order on the last one. It was a square matrix. Again, it's a 3 by 3 and a 3 by 3. So we knew it could be done. But here I really, they're not matching. I should make sure that it is possible. Here this is a 1 by 3 matrix, and this is a 3 by 1. And so those inner numbers match. That tells me it is possible. So let's go ahead and do the multiplication. We're going to have 1 times 4, which is 4. Notice I'm continuing to move across my row, continuing to move down the column. -2 times 3 is -6. And then 5 times 0 is 0. I've completed my first row. I've completed my first column. there's nowhere left for me to do. There's no other columns for me to multiply this by. There's no other rows for me to multiply this by. I'm done. This is going to be a single-celled matrix by the time I'm finished. My answer is simply the matrix with the one element, -2. It's kind of odd. Let's see what happens if I were to switch the order. B times A. That means I'm doing the 4, 3, 0 times the 1, -2, 5. And again, to check to make sure that it works, I have a 3 by 1 matrix here. I have a 1 by 3 here. And it says inner numbers do match. This is possible. So let's multiply them together. We have a 4 times 1. That is 4. I have finished my row. I've finished my column, so I must have finished that cell. But I still need to multiply this first row to the second column. 4 times -2 is -8, but that has to now be its own cell. It has to be a new cell because once we complete a row and once we complete a column, that ends the cell. Then we still have to multiply this 4 by 5. 4 times 5 is 20, but again, it is its own cell because we completed the row, we completed the column. We've now finished with the first row. Let me move to my second row. 3 times the first column, 3 times 1 is 3. I've finished my row, I've finished my column, I've finished the cell. I still need to multiply to the second column, so I'm going to go 3 times -2 is -6, and 3 times 5 is 15. Notice each of those is individual, they pop right into the cells. Then I have the 0, 0 times 1 is 0, finish the row, finish the column, finish the cell. 0 times -2 is 0, and then 0 times 5 is 0. Very different answer than what we just got a second ago. Very different. Completely different numbers, but completely different size as well. Let's see if multiplying these other ones in the same order matters or not. So here we got an answer. Let's try switching it. Just for the fun of it, let's make the order opposite. Maybe it didn't work because the matrices were different sizes. Maybe that messed something up, but maybe it should work if we had the same size matrix. So I've rewritten my two matrices here. I'll multiply these together. So we have -2 times the 1 is -2. We have to move across the row, across the cell. I'm not finished yet, so I have the 0 times 2, which is 0. Now I've finished my cell. I still need to multiply that first row to the second column, so I'm going to have the -2 times the 3 is -6. Move over, move down. That's a 0. I finished my row, I finished my column, I finished my cell, and there's also no other columns to go to. I still need to do the second row, so I have 4 times 1, which is 4. Over and down, 5 times 2 is 10. And then I finished the row, finished the column, finished the cell. Moving over and across, I'm starting a new cell for second column, second row, second column. 4 times 3 is 12, 5 times -1 is -5. And combining these elements, we get -2, -6, 14, and 60. Absolutely the correct answer if I were to do this multiplication in the opposite order. Completely different answer. Which brings us to this very important point. Matrix multiplication is not commutative. AB does not equal BC, with a few exceptions. AB does not equal BA, rather. AB does not equal BA. We cannot switch the order of the matrices and expect to get the same thing. Occasionally it works out. A little bit of random chance in them, not really random chance, there's things going on. So it could be the identity matrix, a matrix full of ones on the diagonal. It could be related to inverses. There are special cases where we would get that it is commutative, but those are just specific cases, not a rule. AB should not be equal to BA as a general statement. Notice, too, that the sizes might change. So not only do we not get the same numbers like we saw with that square 2 by 2 matrix, but the sizes are completely different. So I want to come back to this idea of order. Here, here they are. I have my orders here. We had a 1 by 3 and a 3 by 1. I multiplied those together, A times B, 1 by 3 and a 3 by 1. And we said we could do it because the center's numbers matched. Yes, we got a 1 by 1 matrix. Here, 3 by 1, 1 by 3, center numbers matched, said we could do it. We got a 3 by 3 matrix. With our square matrix, we had a 2 by 2 and a 2 by 2. We multiplied these together, the inner numbers matched, the outside numbers, we got a 2 by 2 matrix. The order tells us a lot about the result that we're going to get with multiplication. The inner numbers have to match, and the outer numbers are going to be the result. So if I said multiply matrix A with order 3 by 106 and B with order 106 by 19, and we had A times B like this, that's going to tell us the resultant order must be a 3 by 19. The inner numbers matched, we would get these outer numbers. If we did B times A, so if we tried to do the commuting, right, if we were trying to switch the order, it would actually be impossible because now those inner numbers wouldn't match. If we did a 106 by 19 and we multiplied that by a 3 by 106, those middle numbers don't match. This is impossible. So not only trying to commute matrices will it not give me the same answer, sometimes it becomes absolutely impossible. The associative property, AB times C is equal to A times BC, that actually is still true provided that each of these is possible. So the inners for B and A and B would have to match. That would give us a result of the start of A, the finish of B. The B and C would have had to have been possible too. So as long as this was possible, one side is possible, the other side is guaranteed to be possible, this will be a true statement. The multiplicative identity. This one's interesting. If we were to take a matrix and multiply it by a matrix with ones on its diagonal, however many we need, and zeros everywhere else, that would actually get us back to A. Now, when I do this in class, I always ask for what do you think the multiplicative identity would be. Let's start with the matrix 3, 1, 2, 4. And I always get the answer of, well, it has to be a matrix full of ones, right? Let's see what happens if we were to multiply these two things together. We'd have 1 and 3 more. And already we can see that's not going to give us what we started with, but just to finish it out, then we'd have a 1 and 3 more. And then we'd have a 2 and 4 more here and a 2 and 4 more here. And so we'd get a matrix of 4, 4, 6, 6. Obviously not the same. We've done the multiplication correct, but it's obviously not getting back to where we started. Notice what we wanted. We wanted the first element, we wanted the second element. We wanted the first element, we wanted the second element. We wanted the 1, 3, 2, 4, which means we want these elements to zero out. And that's why our multiplicative identity always has ones on the diagonal and zeros everywhere else. It can't just be full of ones. That wouldn't work. The other interesting thing about this is this means that we can only have a multiplicative identity for square matrices. And so non-square matrices don't have identities. So kind of leading me to believe that square matrices are, not that we can always have a square matrix, but if we're going to choose how to design a scenario, square matrices are kind of nice. That's useful. Let's just, for the fun of it, I want to multiply by something a little different. Let's say we had that same 1, 3, 2, 4. This time I'm going to multiply it by a matrix of 0, 1, 1, 0. So we have the ones on the opposite diagonal. So our result, we would have 0 plus 3, and then we'd have the 1 times 1 would be 1 and 0, and then we have 0 and 4, and we'd have 2 plus 0. And so we get a matrix 3, 4, 1, 2. And that's absolutely right. Notice, what did we do? We flipped it over. We reflected this thing. So this brings me to the last point, right? When we went into this, I said the only reason we've used matrices so far is for systems of equations. And that's still a very useful application. When are matrices used? Matrices are used for data storage and convenient data manipulation. Think of any Excel sheet ever. That Excel sheet naturally has all these columns and rows. That is a big matrix. We just don't call it a matrix, we call it a spreadsheet, but it's a big matrix. In fact, what you're looking at right now to watch this video is a big matrix. Every image that you could possibly have seen is a matrix. And let's take a very basic image. So here I have a 3 by 3 matrix. I'll put blue here, here, and here. I'm going to put red here, here. I'll put green in the remaining cells. So whatever this picture is of, right? We have maybe some land over here, we have some water, maybe this is representing a boat, I don't know, right? Whatever the picture is, this is a very simple picture. If I wanted to turn this into a matrix, that would be quite simple. Let's just assign numbers and colors. Let's say that 1 represents blue, 2 represents red, and 3 represents green. Well, clearly this is a 3 by 3 matrix. My blues were here, here, and here. My red was here and here. And my green was here, 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 and here. And we have just turned this image into a matrix. Now, of course, this would be a very simplistic image. It wouldn't give you a whole lot of detail. If you think about how TVs are advertised, they advertise on the number of pixels. That is one of the things that they advertise on. It's telling you how many little cells here. So a 9-pixel TV would be pretty worthless. Pixels now, I think, are well over 1,000 because we really want to see that level of detail. And in fact, harder on new computers, but if you really stare at old TVs and old computers, you can actually see those little boxes. Very clear what those cells are or where they are. And so then the TV is just reading it saying, well, these numbers tell me to turn on what colors. And these colors deal with the number of colors presented in the TV. So this would be another thing that's advertised on the side of the box. I think it's called PPI or something like that. The number of PPI. So again, if we had, say, that 1024 display image, that's representing that there are 1024 colors. So now I think they're getting up to about 2,500 or so. And so the more colors, the more detail you're going to see in your picture. Again, very simple here versus, if I wanted a better picture, maybe I'm going to use some different shades of blue. I want, for the rougher water, maybe it's a darker blue up here. And I can start incorporating that with more and more colors in my picture. So every single TV screen or every camera screen or cell phone screen is just a big matrix that's turning on and off these colors. And that's why some calculation like this can be so useful. What if I'm looking at a picture and I'm about to set my profile status or whatever device I'm using, and I want that picture to be reflected for whatever reason? I want it to be flipped over. Well, on the computer it's real simple. We just say flip image or rotate image. What the computer is doing is it's taking that massive matrix and it's multiplying it by the matrix it knows will do the given operation. So anytime we have those zeros on the primary diagonal and the ones on the opposite diagonal, that is giving us that reflection quality. We can come up with matrices to do twists. We can rotate images. We can really manipulate them. If we wanted to just say darken all the colors, well, if I had multiple shades of blue and I say I just want to darken all these shades here, well then let's just add 1 to each of those and that'll move me up to the next blue, or however I've set up my matrix. So we see matrices all the time in our everyday lives. We just don't think about them as being matrices. Other applications of matrices, data storage, images, also encryption, especially more so in the past, still in the present. They use it more in that data storage way rather than actually encrypting data now. But we saw with matrix multiplication, this is kind of an obscure idea that we take these two things and we multiply them, and notice how we don't end up at anything close to the original picture. So the 3 has turned into a -4, the 1 has turned into a 13, the 4 has turned into a 34. There's no rhyme or reason between where those things went. There's no good mapping property. So if you think about your kindergarten basic encryptions, where it gives you a little message, it has the numbers 3, 2, 5, and then 7, 9, 4, right? You guys probably saw this at some point. And then you're supposed to figure out, well, 3 is actually standing for T, and then 2 is standing for H, and then 5 is E. And so we can figure out this is a D, and then we can do that for all the letters. Just kind of checking, guessing. You did this probably back in literally elementary school. A long time ago, you probably saw this in some way. And the problem with this basic encryption, it's nice if you just want a challenging message you can send to somebody real quick. It's real hard to break in that instant time, but it's not great if you have a lot of time to sit there and play with it, because if you think about maybe going to war, if your enemy has a couple days until you launch your invasion and they're sitting there trying to crack this code, they're going to do it. And this is what we saw. We still see it, but especially in World War II, the British got very good at cracking codes, and the Germans got very good at making codes. They created this thing called the Enigma Device. And what that was doing is it's implementing kind of this matrix system. There's not a simple way to say that every single time I see a -4, it can be related back to a 3, because depending on what that key is, it changes it to something completely different. the numbers are never going to align. So now here we had ones on the diagonal, yet none of those ones matched, except for there are 4, and that's just kind of pure chance actually. They never matched. This one I didn't have any repeated numbers, but the numbers become unrecognizable. So it makes it a much harder encryption. You have to encrypt, what does this 3 stand for? Does it stand for an A, B, or C? And then I also have to know this entire encryption key to be able to undo it. And so the Enigma device did this very quickly and very efficiently. So without this sort of code cracking ability, unless you had those keys sitting there, you were never going to get it. And so the British were able to get their hands on an Enigma device, and between that and their code cracking abilities, they're able to figure it out. So matrices are still used in basic encryptions. As the British determined, you can crack this still. It just takes a lot longer, and really with the advent of modern computers, it made it a lot more efficient. But now we use other things too. We use prime numbers actually a lot of times in encoding, because prime numbers you can't just multiply to get to them. It's the whole point of a prime number. So there's a lot of value in knowing the largest prime number. Getting away from the topic, but those are some of the applications of matrices, and there are some of the ways that we can use them. Hopefully this has been helpful. We now see some operations of matrices, and we can also see their applications.